Welcome back, everyone. This is part 3. We're looking at the design of emission systems, the emission part of irrigation, the fun end where water actually leaves the pipes and reaches the soil and reaches the plants. And that's really where the exciting stuff starts to happen. As always, very happy to have Bruce Naka with us tonight to fill us in on a lot of the details. Would like to thank our funders, of course, the Climate and Agriculture Initiative BC, the Kootenay Boundary Farm Advisors, Columbia Basin Trust, and a whole lot of support from federal and provincial levels. Also, big thanks to Andrew Peterson from the Ministry of Agriculture and Ted Vandergulik from the Partnership for Water Sustainability. Those two guys are real gurus in irrigation, and they've supplied a lot of information and ideas and input in general to the entire world of irrigation in British Columbia, but also specifically to this presentation. Please let us know if there's anything specific you want to know more about. Bruce, thank you so much for being with us again tonight. What we're going to be looking at is application rate, how quickly you want to put water on your soil, depending on a number of factors, the efficiency of different systems, and then really crucially, how evenly, how uniform you can get that water across your land, depending on the application. It's complicated as usual, but Bruce will do what we can to bring it down to earth for us. Thanks very much, Bruce.
Good evening, everyone. So today we're talking about emissions. In today's presentation, we want to focus on specifics of how to apply water efficiently and factors which impact our ability to be efficient. Okay, so some of the issues which have an impact on our ability to be efficient in our watering obviously is waste from runoff. So we're talking about waste. Runoff is always an issue. If you're applying water at too heavy a rate, obviously you're going to have runoff. This session, we're going to be looking at what the right rate would be. Leaching, and leaching means it's going to leach out of our root zone, so it's not effectively being utilized by our plants. So again, it's a loss. Scheduling, some people in their schedules are probably trying to make good and sure they have enough water, but a lot of times they're putting on so much water that the soil can't accept it, and it leaches away. Leaching causes leaks, I should say, cause both of these issues that we've discussed here. Okay, next. Okay, I'm going to look at, we're just going to have a little bit of a review here. The emission devices that we are looking at, we're looking at everything from drip irrigation, type of emitters, to spray irrigation, and then we're looking at more efficient types of sprinklers that are being utilized versus the brass impacts right now. In pivot systems, we're looking at the drop-down pivots. And then, of course, we have the big guns which you use. So how do you select these things? Well, you're going to look at the crop height. You're going to look at the water demand for the crop. You want to look at soils and terrain, and that's going to help you in your selection process of what type of device you want. Okay. Application rates. Now, keep in mind that your various types of irrigation, you're going to be applying the water at a very significantly different rate. So obviously with a drip irrigation system, you're applying water at very slow rates, anywhere from 0.1 up to 0.2 of an inch per hour. On the flip side of it, you're looking at the big traveling guns where you have from 0.5 to 1 inch of water being applied per hour. And then in between, you have your pivots, your wheel moves, and your micro sprinklers. Micro sprinklers are micro in the fact that they're applying water a lot slower than your average sprinklers are. Your average sprinklers are in the 0.3 range. Your micro sprinklers can go right down to 0.15, but up to 0.4. That's a little bit of a misnomer. Most micro sprinkler systems we're utilizing are in the 0.15, about 0.1 to 0.17 in most applications I use micro sprinklers on. Next. So other things that impact our application rates, we want to look at the soil texture. How fast can your water accept that soil? You want to look at the cover. You want to look at the slope that the land is on, and then the potential runoff and erosion. So just a look, if you have a sandy soil, as the chart on the right would show you, if you have a grass crop on it. You can accept up to 0.75 of an inch per hour. With a bare soil, 0.4 of an inch. And then of course you go down all the way to the other end of the table with a clay soil, you cannot exceed 0.25 inch per hour. And with bare land, it's going to be 0.1. So this is going to be your checkpoint. So when you are going to determine what your application rate is, so let's look at our sandy loam type of soil. In a sandy loam type of soil, because it's the water flows through it easier, you have the liberty on a grass to use an application rate of 0.45 inch per hour. Bare land would be a 0.25. So in the case of the sandy loam, if you were looking at some heavy water application device, such as a traveling gun or something like that, in the sandy soil, you could probably use that in a lot of the times. But if you had a clay soil, you'd have to look seriously at how you're going to do that. You'd have to really speed that gun up to get your application rate down. Okay. So slope has a very critical effect on our application rates. So if you have a flat piece of land, here we're looking at the sandy loam type of soil again, you're going to be at 0.45 inches per hour as the maximum application rate you could use. Now let's throw a 10% slope in there. With a 10% slope into that factor, you're going to be looking at a 0.34 of an inch per hour is your maximum application rate. Then when you increase it more to a 20% slope, then you're all the way down to 0.23 inches. So you really, sloped areas, you really want to look at that. You want to possibly look at if there's the direction you're running your lateral in, if it's a new piece of land, is that the right direction, or how could you minimize it? Could you have a header line in the middle so you're maybe all of the slope wouldn't be in one section? You'd have to really evaluate the best way to do that. Next. So just to review again, application efficiencies, if the system is being run correctly, and that's a caveat, if it's being run correctly. And this is the percent of the water that's reaching the roots. Well, in subsurface drip irrigation, it's the highest percentage of at 95% versus above ground drip is at 92%. Why the difference? Well, the difference obviously is subsurface, you're not going to have the evapotranspiration rate you would have above, and the water will more efficiently move through your soils below. Pivots are probably the most efficient other than drip irrigation. Pivot with a boom, the drop down pivots, they are up to 80% efficient. Boom, for those of you who haven't heard of it, booms are a conversion device which some people are utilizing onto traveling gun sprinklers, taking the traveling gun sprinkler off and mimicking that with like a mini pivot. That would go in lieu of that. Stationary gun, now that's the sprinkler head that isn't traveling, so it's stationary, is the most inefficient at 58%, and traveling guns are at 65%. This is, as we were discussing before, efficiencies with their subsurface drip, sprays, inline drip, 92 to 95% efficiency. Sprinklers, your K-line, you may not have seen K-line before. K-line is a product line that was developed in New Zealand, I believe it was, and it's something that you can drag behind your ATV, and it's a fast, effective way. Some people think it's more efficient and quicker to set up the wheel line or something like that, because you can just drag that behind your ATV, so that is an option. Under tree sprinklers, 75% efficient, and sprinklers just used on a hand move system would be 72%. Pivots with a low pressure drop, as we were suggesting, is at 80%. Dragonline, who we have discussed it before, but a Dragonline system is a conversion that they've utilized in the South, down in the States, whereby if you have an old pivot system that had maybe brass impact sprinklers or something like that off of it, you can convert that to a drip irrigation system and be dragging that pivot around like that. So it's energy saving, as well as something that could be more efficient. And on certain crops, it's very viable. It's very important to note that everything that we're assuming with the efficiencies is based on an ideal world. The ideal world meaning that the nozzles that you have on the system are uniform in their sizing along the line as much as possible. The nozzles should be new. If they're worn, you know, you can, if you were to try to size some of your nozzles out, you would find that after a couple of years, depending on your water quality, of course, that your nozzles, which may have started out at a 1/4 inch nozzle, could dramatically be 30% higher than that. And so your efficiency along that line is significantly different. The pressure that you have to operate on, they create charts to show you where you're going to get the maximum distances from your sprinkler heads, and when you're spacing it, it's important to base it on that. You don't want any leaks, so often you see some large leaks on lines and that obviously that's going to affect your efficiency as well. Emission calculations. Now here's, at this point, I want to point something out. Obviously, when we're looking at calculating out the amount of water that you're applying, when we're looking at sprinkler heads, we're looking at sprinkler heads which are giving you application rate in inches per hour, and it's based over an area. So if you have sprinklers dependent on the spacing they're at in the nozzle and the sprinkler that you are utilizing, you would calculate that out with a formula. So you would have an application rate over a given area. In this case here, we're looking at sprinkler heads that are covering a 1,600 square foot area. We're applying water at the rate of 0.18 inches per hour. So it's broadcasting it over an area. Drip, on the other hand, and it's one of the reasons perhaps why drip is so efficient, is what are we doing? We're addressing the amount of water that we are utilizing for a given plant or tree. If you're applying the water to that, we're saying, how much water does that specific plant need? We have crop coefficients, which are factors based on their ability to cope with evapotranspiration rates in that and be a little more forgiving. Certain plants, for example, grapes, require a lot less percentage of ET than say a cherry tree or something like that. So in drip irrigation, we're looking at 90% on our efficiencies, but we're looking at a system that is addressing the water specifically to that plant area, not in the area in the middle of the panel. So drip can be efficient. In saying that, and I'm not advocating you should be doing this, there have been a lot of trials where they've used drip irrigation on everything from a lot of fields, hay fields, pastures, and the likes of that down in the south again, because of maybe in this case here, lack of water availability. It's one way to address it. Next, please. I should have mentioned on the last slide, you don't have to go back, Andrew, but our next session is going to be on scheduling. So in that scheduling, we're going to go over for your drip irrigation, how much water you need for a specific plant, how that formula comes out, and you know, if you're interested, we can go into a lot more detail on that. But that's getting down to the nuts and bolts of what we need to know, the tool, that how much water do we need to apply. Uniformity, guns, sprinklers, and micro sprinklers. That's good, thank you. Next. So what's going to affect your uniformity of your sprinklers? In other words, if we do everything just right, so we have no friction losses along our pipeline, it's a relatively flat field, how can we go wrong still? Pressures have a big impact on the distribution of water coming out of it. For example, if you run too high of a pressure, those sprinklers are going to mist. They're going to be throwing out a very small droplet of water that's going to atomize, and it's going to minimize the throw of that sprinkler. So it's very inefficient in a lot of applications. A lot of people think the higher the pressure, the farther that sprinkler is going to go. But the farther that sprinkler will go, maybe it could be going a long way, but it could just be a little tiny droplet of water that's flying like crazy and isn't efficient, because it depends on where that droplet of water hits the ground, and is it being distributed evenly? Well, that doesn't happen with high pressure. Medium pressure, if you look at if you were to look at a performance curve on any sprinkler head, I always try to look at the middle of the chart. And you'll find, it'll vary, a half-inch impact sprinkler or a micro sprinkler or something like that. It's going to operate at 20 to 35 pounds pressure. 30 pounds is what I usually use as the optimum mid-range pressure. When you go up to a bigger sprinkler, 3/4 inch impact or larger, you want a minimum of 40 psi. So at that pressure, your droplet of water is going to be a medium size. It's going to be the best for distributing your water. When you have too low a pressure, and I mean, it's quite obvious when you have that, you have these great big droplets of water. They come out of the sprinkler head and they don't go very far and they drop straight down. It's very volatile and where that water is spreading. So we're looking at having that mid-range on that sprinkler. If you're going down a long row of sprinklers, the best way to check your pressures along that line is with a pitot tube. Pitot tube is just that little hook device that'll fit right underneath a pressure gauge, and you can go around and get wet. I've watched Andrew in action testing on wheel moves, and he came out like he had 2 showers by the time he was finished. But that's the best way to figure out where your pressures are along the line. Next. Okay, what are some of the tools that we can utilize? So if we're in a situation where we have too high a pressure along a given line, one of the devices that you could utilize are pressure control underneath the sprinkler heads. You could, depending on the length of the line, if you wanted to get elaborate on some systems, they have pressure regulation. We do a lot of times in drip irrigation right on the beginning of each zone. But depending on the length of a lateral and a lot of other things, you may need to have individual head control. Then, of course, undulations in ground terrain are going to affect our pressure, are also going to affect drainage after the system's off. So that's something else that's going to impact how evenly our water is being distributed along a given line. Next. So what should you do in some of these circumstances where we have the pressure? We've already addressed that. We can use pressure regulation or flow control regulation underneath each of the sprinkler heads. Relatively inexpensive method of doing it. Also, you can get check valves. The check valve can go underneath the sprinkler head and it's going to affect your low head drainage to a point. I say to a point. For the next slide, please. Okay, I'm bad. It's not the next slide, but we'll get to it. Excuse me. Spacing of your sprinklers obviously is very important too. Obviously, the spacing has got to be consistent along a row. So if you have decided on a 40-foot spacing on your sprinkler heads, then you want to make sure you're consistently at the 40-foot along that line. If you have typically head-to-head spacing, that I'm sure that's a term that majority of you have already heard about. Head-to-head spacing means where the spray of one sprinkler head comes up to is where your next head should be. So that from one head to the next, the water is hitting from the opposite one into it. Acceptable overlap in agriculture that we were utilizing for sprinklers typically is 60% of the diameter of the sprinkler based on a zero wind condition. So in other words, if you had a 40-foot radius on that sprinkler head, you have an 80-foot diameter. The 80-foot diameter, 60% of that would be 48 feet. So with a sprinkler that's got an 80-foot diameter, you would not exceed 48 feet on your spacing. If you have situations, if you're looking at, say, a wind condition of 14 to 15K an hour, you might want to tighten that up to your head-to-head spacing. If the wind is even stronger than that, you may want to go as tight as 40% of your diameter on your spacing. One thing that obviously is important is when you're laying your sprinklers out on a given field, if you're cognizant of the wind, there's always going to be wind in some certain circumstances, but if the wind is typically coming from a given direction, and it can be fairly strong at specific times of the year when you're irrigating, you may want a strong space in those areas there, because if the sprinklers from the wind direction is going to be blowing them further, let's say we were looking at a spacing, an average of 50 feet. So if you were looking at a 60 by 40 spacing with a 3/4 inch impact, you would probably want to go to the 60 feet taking the strength of the wind to adjust that distance and then be tighter at 40 feet in the other direction. But wind, you always got to be cognizant of wind when you're looking at your overlap situation. Okay. Some other tricks of the trade. I'm not going to talk too much about rectangular, but triangular spacing is a more effective spacing method than say a score pattern. Why that is triangular means that it's equilateral triangle, so that the distance, if you were to go between two heads on a line, the distance from that point halfway between the two heads to your sprinkler head itself would be the distance. So if you were at a 50 by 50 spacing, the distance between the two heads to the point of the next line over in that triangular fashion is the 50 feet. That's the important part. Next. Okay. Well, traveling guns, I think you will recollect, other than the stationary guns, is the most inefficient of all of the types of sprinklers for a couple of reasons. Traveling guns are often, because it's a large gun, run at higher pressure, even though they're higher volumes of water. That has some effect on the size of the nozzle. But the other thing is that and I can't honestly give you the correct answer for this right now, but for some reason, we are always stretching our spacing on traveling guns. And typically, even if you look at the agricultural manual, it shows a 65% of wetted diameters of spacing. So typically in utilizing traveling guns, depending on the size of the gun, you'll see lane spacing is up to 200 feet. Where if we were looking at a sprinkler head that say had a 300-foot radius or diameter, you wouldn't be at 180 feet at 60%. So they are stretched a little bit. I don't know if it's because it fits in easier with the aluminum pipe lengths and everything like that. But that is one of the reasons why traveling guns are not as efficient. You can look at something on one of the other issues with traveling guns is the fact that when you are running those systems, when they get into the end of the run, they stop and they're spraying on one spot. If you don't have an automatic shut off on your pump, they will keep on running in that last position and put a lot of water at the end of it, which a lot of people complain is a waste of water, which in fact it is. If you shut it off, you're going to save that water and save your electrical bill. This is something that isn't always taken into consideration, but one should be very cognizant of it. We see it a lot in vineyards, where a lot of vineyards are putting in two irrigation systems, one being for your drip irrigation for irrigating, and then they're putting in an overhead system, which they're using for maintenance of a cover crop, so sometimes cooling. I know you always think that you want heat in grapes, but not always. So you're looking at a lot of areas where you're putting a part circle sprinkler on the end of a row where you only need it the one way, and then you're going to full circle on the other ones. The match precipitation is something turf irrigation we're always using, but match precipitation is very key also in agricultural irrigation. So if you have a zone where you have a whole series of full circle sprinklers, and then you have part circles on the end, or if you have a row of sprinklers on the very outside of a field, where you have no desire to irrigate beyond that, say it's on a fence line or something like that, if they are on the same circuit as another row of full circle sprinklers, you should be reducing the size of the nozzles in the part circle heads in order to equalize that application rate as you would have on the full circle. So in the example here, if you had a 5/32 nozzle, you'd be looking at say a flow of 5 gallons per minute, and that's what your full circle is using. So we want to go down to something that's putting out about 2.5 gallons per minute in order to facilitate that application rate. So a 7/64 nozzle would be doing that based on that spacing. The one thing you got to keep in mind on all this is you want to look at your performance chart, because as you reduce your nozzle sizes, obviously, in most circumstances, you're shrinking on your distance, the throw. So just make sure it isn't stretching it too much. Okay, now here's some things you got to look at when you're choosing the right nozzle. So what do you want to consider? You want to consider what rate can I apply it at? In other words, what's my soil? Do I have a clay soil? If I have a clay soil, I don't want to be applying water too heavily based on the spacing I need. What spacing am I going to need? If it's a row crop, then you may be confined to posts in a row, or the spacing between your rows, because you want to be along a row. You don't want to be in the middle unless you're using a pop-up sprinkler head. What pressure do you have available? And what flow do you have available? So typically someone such as like myself or Andrew, who would do an irrigation design, we're going to try and design it with the best tool for the market, the best emission device that we could utilize. So if I am looking at a circumstance, call it, let's say we're working on a nursery or something like that, and we have a row every 8 feet. So we want to hit it with some sprinkler heads. So you want to come up with something that's a factor of the 8 feet, so that we're in that row. So let's say on every 5th row, we would have it at 40 feet, would be our spacing on that. If it was every 4th row, you would be at 32 feet. So we want to look at it. We want to look at our client, for our client's sake, we want to have the best product for the job without going overboard, utilizing one sprinkler. For example, if we were doing that nursery and we decided to go to 32 feet, we're going to be having that many extra rows of sprinkler heads, where the 40 feet will work properly. We're looking at 60% of the diameter of that sprinkler head. So we're looking for a sprinkler that's going to match for a 40-foot spacing. And then we want to look at an application rate that's going to adhere to the soil that they have. So then we look at it, we'll go over to a chart. So you look at a chart and you look at the models of a sprinkler, and at the top of that chart, it says PSI. It's got a red circle around it. I suggested a little while ago, what pressure do underground or half-inch diameter sprinkler heads operate best at? 30 PSI is the number we came up with. So if we look at 30 PSI, it's not in the middle of the chart, which was something else I was advocating, but 30 PSI is inadequate for a head to operate on. We're using 2.17 gallons per minute. Below that, it shows you the radius of the sprinkler. And this particular company doesn't give you a specific number. They give you a range, 34 to 37. So that fluctuates based on the pressure that you have. You get a little higher pressure, you're going to get a little further distance, and that sprinkler head is using a little bit more water. So you have to determine what the average spacing is. If it's on a hill or something like that, we're going to be gaining pressure. Obviously, the heads lower down are going to be using more water. So at that point, should we be considering using a flow control or pressure regulation underneath the sprinkler head? These are some of the things that you want to look at. So the slower that you apply, and there are caveats on this as well, but the slower that you apply water, the less water you're using, and therefore you're going to have fewer zones, bigger zones. So from a cost factor, that's good, but there are other things that you want to look at on that. If you have variances in soil between that, soil profiles, you sometimes, if it's dramatic, you may want to break up and have additional zones based on the differences in your soil. Somebody would say, well, geez, then I got all these extra little zones. What am I going to do? Well, if you go to a control system, an electronic system, for example, you could utilize it, and you could maybe have that whole area turning on at the same time on 2 different zones or 3 different zones if it's required, but they could shut down at a different time, dependent on the application rate based on the soil. So it can be done. Is it more complicated? Perhaps a little bit, but look at how much more efficient it can be. Next, please. Right, micro sprinkler. Micro sprinklers, there is a place that starts to get confusing when you're looking at micro sprinklers, and they say, well, what about, is this drip or is this micro? Is it a sprinkler? Well, the answer to that is when you're calculating out your flows utilizing a micro sprinkler is a movable sprinkler that's throwing water around, emulating closer to that of a sprinkler head than a spray or drip would be doing. So we utilize the micro sprinkler booklet to determine how to calculate out the application rate. So here we're looking at, again, we have a couple choices. We're looking at the flows in micro sprinklers are always in gallons per hour. And your distances that you're looking at, if most of the time micro sprinklers are used in a nursery or a tree row type of application, tree applications. So we're going to be looking at the spacings necessary to facilitate what we need. The one thing I will caution, you can see this one here is a pressure compensated micro sprinkler. Years past, pressure compensated micro sprinklers, there's been some challenges for a couple different reasons. The diaphragm that was in them was something a little bit more volatile. The life expectancy wasn't that great, number one. Number two, they're a lot more expensive than a conventional micro sprinkler. So for those two reasons alone, I would caution against it. But the other reason that you have to, anytime you're looking at any micro type of equipment, be it a micro sprinkler, be it a micro spray, be it a drip irrigation, keep in mind, the smaller the flow rate you go, the smaller the orifice size, the more critical the filtration necessity of it is. And so I always look at that, depending on the area you are. If you have water, very turbid water, you want to look seriously at it. And if you're going to go to micro sprinklers, be prepared to be more elaborate in your filtration requirement. Next, please. Uniformity with drip and micro sprays. We're going to look at how efficiently micro sprays and drip are going to be. We're dealing with lower pressures, so it's not as forgiving necessarily as sprinklers will be. We want to look at the patterns. What happens when you're using drip equipment is that you're looking at that water being applied to a given area. What happens to that water when it enters the ground? Depending on your soil, it has quite a significant difference. On the left-hand side of that table there, we're looking at surface versus subsurface irrigation. And you're seeing that with subsurface irrigation, you're getting better spread of water going through on the subsurface type of a system generally. But looking at the chart on the right, we're looking at a sand versus a clay soil. And you're looking at it for a period of time. What happens when you hit a sands soil? Water being applied usually will go straight down into the ground like that. So you'll see over a 24-hour period of time that your water has not spread that wide. At its widest, it's gone a foot on either side, 2-foot spread. You go to a clay soil now, it holds the water better, but it holds the water better, but you can't apply it too fast because otherwise you're going to have puddling and the likes of that. So you see over that 48-hour period of time that you are getting a lot more spread in your width of what it's going to cover. I will say one thing: if you utilize a sand soil, the art of how you might want to get more spread on that is you may go to a higher application rate of an emitter in order to facilitate. You could hit a point where that water you're going to get more spread out of it because you're applying the water at a higher rate than if you're going with a lower one that's going to go straight down into the ground. Next, please. So drip patterns. What are we trying to do in drip irrigation? Well, one of the things that I know in earlier years with the drip, when people were starting to consider utilizing drip irrigation for crops that before were not having it, for example, apples, the Okanagan and the Creston area and that. You had old trees at wide spacing. You were looking at a 20 by 20 or 25 by 25 with an interplant type of spacing in these orchards. So they were typically being irrigated by sprinklers. Sprinklers were affecting the whole root area. The roots were big, they were established. And then along comes drip irrigation. Drip irrigation, you found up to, I think on average, 4 or 5 years, where it is, well, maybe that's a little long, 3 to 4 years, an effective drip irrigation system could work, but if it's stressed, there was a lull in production and they found on going to drip irrigation. But drip irrigation wasn't done the same way as it is today. Drip irrigation was doing, if you had a tree, you put an emitter on either side of the tree and it effectively watered the roots. But the roots were spread a lot further in a lot of those older trees, so they weren't getting the entire root zone. One of the things that we've gone to more so in years progressing is the fact that we try to create a wall of water along the line. So irregardless of the spacing on that, based on the type of soil that we have, we want to create a wall of water so we can effectively address that whole root zone. We're not going to get into the middle of the panel. We're effectively going to hit the root zones of those trees along those areas there, and we can minimize some of the stress. Next, please. One tactic that's been utilized a lot, utilizing drip irrigation, we've talked about this a lot, is the fact that if you have a single row of drip irrigation in a system, you're not satisfied with the results you're getting on that. In a lot of circumstances, we've done this in cherries, we've done this in blueberries, where you'll go to 2 rows, each one on either opposite side of the trees. On a brand new tree, they may start out with 1 row, and then as the tree matures, they'll add the 2nd row of drip on the other side. The transition to that is far less expensive, and it doesn't cause a lot of differences in your zone sizing and everything like that when you calculate it out, because your 2 drip rows are probably going to use less water in a lot of instances than going to 1 row of a micro sprayer or a micro sprinkler or something like that, where you need larger piping, more zones and everything like that. So your costs as well as your infrastructure change a lot of times is better for utilizing drip irrigation for that circumstance. Even had circumstances of drip irrigation where we've added, if someone wanted to maintain a cover crop, depending on what you're growing, they added another row of drip irrigation down the center of the panel to try and facilitate that. Had mixed results on that. Okay, lateral pressure. Drip irrigation, as we said before, is running at, we were looking at 30 PSI on under tree type of sprinklers. We were looking at pressures 40 PSI on 3/4 inch and larger types of sprinklers. Drip irrigation, we're running from 10 to 30 PSI in general. But when you're running at that low of pressure, impact of losing too much pressure is obviously going to have quite a difference. So depending on what you're doing, if you have a situation where you're operating at 20 PSI, and if we were operating at like a sprinkler system, and we will allow it up to a 20% loss or something like that on the line, that 20 PSI would be down to 15 PSI. Well, if it's not a pressure compensating, and this is leading into something that I'm talking about, if it's not pressure compensating, the amount of water that's going to be coming out of one emitter to the next between the 20 pounds and 30 pounds and 15 pounds of pressure, it's going to cause significant differences. So if you had one plant that was getting, for example, 2 gallons an hour of water, and then the one down the road was using 2.5 to 3 gallons of water, that's quite a bit of difference in water. So you're not going to have a lot of uniformity there. High pressures, high flow, good pressures, good flow. Elevation changes make a big difference. Rule of thumb, anytime you're using drip irrigation, even if it is pressure compensating, you always want to feed from the high side. You're not going to feed uphill utilizing drip irrigation. So lateral pressure, the best thing for that is pressure compensating emitters. Pressure compensation, be it a puncheon type of emitter, be it a tape, be it inline drip. These are the types of, you can look at anything that's pressure compensating. You're going to get a lot longer line capability, as well as you're going to have a consistent flow throughout that line. Something that is overlooked a lot of times in drip irrigation is the fact that as you have low pressure situations, air is drawn into the line. In a lot of circumstances with significant undulations, they'll have an air vent on each zone. I always say in drip irrigation, you want to be a lot more particular about additions of the air vents along your main line in the area where you have your drip irrigation system. Any significant changes in elevation, etc., you want to put in an air vent. Next, please. Here's an example, like I was talking about a little while ago. pressure compensating versus non-pressure compensating. So 15 psi, that non-pressure compensating emitter is using 2.5 gallons an hour, and then we go up to 25 psi, and we've got 3.1 gallon per hour. So that's 2.5 pails of water versus 3 and a bit pails of water. That's the difference in water, amount of water each of those plants is going to get. Versus with your pressure compensating, you're going to see your curve being very flat. Something like I mentioned a minute or so ago, always keep in mind, whatever device you're utilizing, you want to be cognizant of the orifice size of the emitter. The smaller emitter uses tremendously smaller orifice. Keep that in mind when you're sizing out your operations. Next. Yeah, so this is a classic type of emitter, so non-pressure compensating. We're utilizing that type of emitter. Here it's showing us our orifice size of being a 0.043 inch. So we want to filter up to 10% of that opening size of that. So 0.0043 is the number you come with. And looking at charts in your BC Ag Trickle manual, that tells you that you need 140 mesh screen or sand filter of equivalent to facilitate that. Okay, next. So what is the right emitter? And what do you want to consider? Well, you want to look at the largest row you have, the largest zone you have, slower rate. Again, you're going to have fewer zones, but drip irrigation, you're not going to have a lot of zones anyways. We want to create that wall of water along the line there. So what's our soils like? Agriculturally, unless you're working on a nursery, typically you're not going to be looking at 12-inch spacing. 18 and 24-inch spacing is probably used more than most in the application and drip. Even though charts will show you that your flows can go as high as 60 psi, or your pressures, I should say, never look at a chart that's going to show you that. Look in the middle of that curve, look at a 30 psi for your nominal size on that 18-inch spacing. With a you're not usually going to a 0.9 high flow emitter like that. It's usually more like around 0.6 emitter. That's giving you good middle of the road flow. Sprays, microjets, we're utilizing 2 per tree. We can emulate, as it shows there, the BC Trickle manual is how you would determine your calculations. So what we're looking at when we're using sprays, again, typically is we were looking at a spray 1 or 2 per plant. So we're addressing the needs of that one given plant, just as you would with your drip irrigation. Sprays, again, would be selected based on the radius, the distance they're throwing out, the size of the orifice, I keep maintaining that, and the pressure you're going to be operating at, as well as the arc, half circle. Okay. So how do you know how uniform your testing is going to be? How do you know how well it's going to work? One point that I missed a little while ago, just because I've covered a lot of different things here, but I think it's important. Anytime you were to buy some drip irrigation equipment, inline type of a drip, typically they will have, it may be in their more detailed technical information, but they usually will have a chart which will tell you if you have a 24-inch spacing, your maximum distance based on the size of the tubing, because you can buy it in 1/2 inch or up 5/8 inch or up to 3/4 inch. So in very, very long runs, you may want to go to larger, but typically on a, say if you're at a 24-inch spacing using about a 0.6 gallon per hour emitter, on flat ground, you could go close to 500 feet and have a very consistent flat curve on most of your drip irrigation. But it's a good way to compare the various products that are out there and see how close they are. Uniformity testing. You've all heard of catch can. Catch cans are the way to take it to the next level, to go along a given line, to go through a sprinkler system where you have sprinklers, to see how even the amount of water is in your given areas. How do you do that? You have to have some sort of containers in order to do that. Whatever container you use, you got to be consistent on. They got to be the same size. And this one here on the left, they're showing the typical one that are used for catch cans, narrow cylinder with a big catchment area on the top of it. And it's got graduated marks on the inside of it, so you can precisely determine what the amount of water that is in it. Using a tuna can or a coffee tin or anything like that, I've used coffee tins, for example, but how accurate are they going to be at those marks so you know exactly how much water that is in there? If it's a tuna can or something like that, and you've gone to the trouble of going through it, determine 1 liter of water is at this ring around the tin, and sometimes it does work. You can do it that way, but you want to be accurate in your readings. You want your cans, whatever you're utilizing, to be flat on the ground. You don't want them to be on an angle, so someone's going to pour out. You just want to make it as consistent as possible and as foolproof as possible when you're setting up your catch cans. Next, please. More cans, the better the results are going to be. So here's how you do a layout. Pardon me, for sprinklers. So you have a given area. The yellow dots denote the grid of your catch cans in that area there. So in those areas there, where are you going to put catch cans out? You want to put some at the beginning of lateral lines, in the middle of, so you want 4, a minimum of 4 at that location there. You want to go somewhere in the middle of your irrigated area. And you may want 2 different rows of them for whatever reasons. There might be some differences in that, and obviously then again you want some at the end of the row. If you have elevation changes and things like that, you want to address that area there so that you have 4 catch cans at least in a lower area and more at least 4 at a higher area, so we can determine over that whole area there the difference in our amount of water that are going into each can. Next. Okay, so in this here, we're looking at also drip irrigation. How do you do a drip can or catch can with a drip irrigation system? Well, a couple ways you can do it is you can put your tuna tins or your graduated discs or your graduated cylinders underneath each of your, in a given row. You could go at random places, one in the beginning, one in the middle, one in the end, more if you like, and just determine over a period of time how much water is in each of them. The trough idea is like a rain gutter where you could collect all the water running down, flowing down a tape, and just collect it at the end so you know how much water is running over that entire line. I would rather see catch cans finer along a given line in 2 or 3 different circumstances. Take that, multiply it by the amount of emitters to determine what your flow of the whole row is, but you still have that ability to see how uniform each emitter along that line is. So yeah, the whole flow of that line, you want to know exactly what the contribution from emitters in parts of the line are. Next, please. Okay, so once we have all this information gathered, the most accurate way that you can compile your results is by utilizing something we call the lower quarter distribution of uniformity. And simply all you're doing there is you're taking your lowest quarter, the average of the lowest quarter of the entire project, and you are taking that, and then you would taking the average of the whole area that you're covering, and then you were dividing your lowest quarter by your average. You multiply it by 100 to get it a percentage, and in this case here we came up with a percentage of 81%, which is good, as you can see on your benchmarks. 90% is where we all aspire to be at, 90 plus, and 70% is the low end. I've seen catch can where the results were 40 to 50%. So that's how wrong things can go. As your nozzles wear, as your spacings vary, as wind affects it, there's a lot of different things that we can look at an irrigation system without even taking into consideration such things as their soils for a given area. So the workings of that system are very, very important, keeping it as consistent as possible. Next, please.
You made it, Bruce.
I made it. Thank you very much. A little bit over our time limit. We have a little bit of time for questions. I hope we gave you some useful information. And as Andrew said, if that session we have in the future has just questions and answers, be happy to do that for you. Thank you.
That's great. Thank you so much, Bruce. Great as always. I've got a few questions here. Irrigating fruit trees in a clay loam soil versus a sandy soil. What sort of differences are top of mind for you? What are you thinking about when you're designing irrigation for a clay loam versus a sand?
I would be leaning towards lower flow emitters.
For which, sorry?
For the clay soil. So we would be looking at lower flow emitters for the clay soil. We would be looking at runtime scheduling, depending on how close to the rate that the soil would accept it. So those would be the key things that I'd be looking at. The heavier the soil, I'd be looking at lessening my flow of my emitters. And the spacing of the emitters could be stretched a little bit more because we're going to be able to create that wall of water easier.
So the main difference then is trying to make sure that you get enough spread in your sandy soil.
Yes, yes.
If you were irrigating with a with a sprinkler system or a micro sprinkler, you might then also be concerned about application rate and puddling with the clay loam.
Probably not the micro sprinkler as much, but you would have that. You know, cycle and soak type of applications where you have controllers, you have the ability to do that. So what cycle and soak is you're taking the total amount of required runtime in a given day, and you might have to break that up into a couple of times if it causes puddling. So you could, if you had 12 zones and you're watering them for 2 hours a day, then you might want to run 12 zones for an hour, then come back and water it for the other hour, for a simple example of how we would do that.
Right. Another question here on operating pressure for rainbird type sprinklers. So I'm assuming just brass impacts. You mentioned 40 PSI. What kind of acceptable range is there? And
yeah, well, 40 PSI was for the larger impacts, the smaller impacts, and now with the Nelsons and the Senningers and the various sprinkler companies that are coming out with some very efficient plastic type of heads, you can go down as low as 25 PSI and have them operate very well. So I like to see any type of, if you're talking the rainbird type of heads, the very minimum I would look at is maybe 30 PSI. Are they going to operate at 20? Yes, but not as efficiently.
right, like the example we were looking at earlier there had the low pressure version of the R2000, which is, I guess, the size down from Nelson's R33, which is the plastic used to replace brass impacts.
Mm-hmm.
If people are looking, they could choose between a higher pressure or a lower pressure of these plastic heads. Would you move over to plastic heads from brass impacts if that's what you've got, or would you just wait till your brass?
If you're going to change it, change the entire system. Don't change just a part of it, because you're going to have a variance in your application. So if you're talking about changing your rainbird heads, I would suggest, if you, like, say you're doing a wheel move or something like that, change the entire wheel move, not just some of the heads on that one. And going to the plastic heads is probably the way to go, because there's going to be a day when we're not going to be using brass anymore.
What would be the tipping point for you to make a decision to, all right, we're switching over from brass impacts to a plastic head on a wheel move? What would be the tipping point for you?
Well, there could be a couple tipping points. Cost of running that system would be one thing. If I was at a position where I was having to replace a lot of my sprinkler heads, that would be another thing. If it was just a matter of consistency and flow, and I had good pressure available, I think the first thing I would do is change the nozzles in my existing sprinkler heads. Look at pressure regulation if necessary, but if I had to change all the heads in the line at that point, or over, let's say half the heads on the line were starting to wear and it wasn't just the nozzles, there was springs going on them, there was arms going on them, I'd say it's time to move on.
Great. Have you done anything with mushrooms? Any mushroom irrigation in the past for you?
Mushroom irrigation. Years ago, yes, I did something for pine mushrooms. Not a whole lot of water requirement necessary. I haven't looked at any large scale mushroom farms, but I would think that drip irrigation probably would be a good choice for mushrooms.
Yeah, that was an interesting one, Philip. We'll look into that one. My instinct was if you were doing some log culture like with shiitakes or something, that maybe a misting or a micro sprinkler system might work well, even a spray system. But one to look into. Another question, and it's it's a good question. Are soaker hoses good for anything?
Maybe to get wet on a hot day. A soaker hose is simply normally just an orifice in a flat hose. An orifice without an actual emitter in it, you're going to have a challenge of a time in order to have efficient operation over that soaker hose. There are different soaker hoses, like a leaky hose and that was made out of rubber and that they've utilized in the past, but I never saw a lot of consistent uniformity through a soaker hose in most applications. If it's just a short run in a greenhouse or something like that, perhaps, but anything like a soaker hose, which is just an orifice in a warm application like that, you're probably going to end up, unless you're using domestic water, having some algae problems, and you're going to have a lot of plugged emitters as well. So I see more negative than positive. If you have a bunch of soaker hose and you take care of it, will it work? Sure, it'll work. But is there better things out there? Yes.
Well, thank you so much, Bruce. I think we've come to the end of the time. Looking forward to next week or 2 weeks from now when we're going to be doing getting really deep into scheduling and figuring out how much water does a plant need, or does an area of plants need, and how often should we be irrigating. So that's going to be a good one. Before we close out, I just want to thank again the funders behind this series, the Climate and Agriculture Initiative BC, the Columbia Basin Trust, and the Kootenay and Boundary Farm Advisors. You can give, if you are a farm in the Kootenay and Boundary region and you want assistance with your irrigation or any other technical production issue, please do give us a call at KBFA. It's a free service for farms in our region, and we're here to help out. So call anytime. Thanks again, Bruce. It was great having you here tonight.
My pleasure. Thank you.